morning. Okay, so what we're going to do this morning is continue with Newton's law of gravity with a couple of applications. Specifically, we're going to show that Newton's law is in accord with Kepler's third law. We will derive an expression for the escape velocity and perhaps look at circular orbits. Just simple things as to what you can do with Newton's law of gravity at high school or early college level. The more advanced stuff, you need the calculus for it. Now recall that Newton's law of gravity gives the force of attraction between any two masses. I'm calling them a little mass and big mass. It could be a person on the surface of the earth, it could be the moon and the earth, it could be the earth and the sun, any gravitating system. There's a force of gravity between all things that have mass. Mass, gravity and inertia are intimately linked, and how that is the case, nobody knows. I'll talk more about it and around it at least when we do general relativity. Now I'm just writing force as a scalar. In part 4 of these courses I'll put in the vector nature of this little formula. Force is mass times acceleration. On the surface of the earth, it's mass times the acceleration due to gravity, and it's given by g times little m big M over r squared, where r squared is the distance between their centres of masses. All things experience that force of gravity. So therefore, without thinking too deep about it, we can cancel the little m's to get the acceleration due to gravity given by gm over r squared, or the mass of the earth equals r squared little g over big G. Cavendish's experiment allows us to find the mass of the earth. Cavendish, 1798. Because he discovered, or he measured experimentally, the G, the big G, the universal constant of gravitation. Now the value of 6.67 by 10 to the power of minus 11 was actually pretty closely obtained by Cavendish in 1798. So now we look further at it. If we wanted to find the acceleration due to gravity on any planet, we could pull in all the numbers if we knew the mass of the planet, if we knew the radius of the planet. And you get, for example, on Earth you would get 9.8 meters per second squared, putting in the m and the r of the Earth. We did that. So let's look at now Kepler's third law. Kepler, Johannes Kepler, German, with a lot of illnesses. The ellipsis law. The first law says that the planets go around the sun in elliptical orbits. Devastated Kepler because they weren't circles. The second law, basically a statement of the conservation of angular momentum, says that when a planet gets close to the sun, it has to speed up in its orbit, and when it's way away from the sun, it slows down from the orbit and sweeps out equal areas in equal time, the orbital radius. Now this is the one we're going to look at. To look at why the orbits are ellipses or conic sections. Ellipses, parabolas, circles and hyperbolas are 4 types of sections of a cone. They come out of the calculus version of using Newton's law of gravity. Newton's law of gravity, using the calculus form of the equations of motion, predicts that the orbits are ellipses. That's the big triumph. Also, the law of gravity in the calculus form gives the conservation of angular momentum. Angular momentum is something you'll study later. But the third law, that's one we can check out using the little bit of algebra that we have. Square of the period is equal to some constant times the cube of the radius. Now for the Earth, the radius is the orbital radius of the Earth. Where is it? The orbital radius of the Earth is 1.5 by 10 to the power of 11 meters. period of the Earth is 365 1/4 days, or 3.156 by 10 to the power of 22. Now that's not right, it's seconds. Let me check that. Oh right, that's totally wrong. I knew it was wrong. 3.156 by 10 to the power of 7 seconds. Sometimes I make a mistake. You'll catch them. They're usually quite obvious. When I'm up here, sometimes I'm not thinking properly. Now, when we have an object in circular motion, it has a certain speed v. It covers a distance of circumference. A distance of 2 pi r, distance. It covers this whole circular distance in its period, the time it takes for a full turn, right? In other words, if this is a path of a planet in its orbit, that's the distance the planet is going to cover in its period. Now the length of a circumference of a circle is 2 pi r, so that's distance. Speed is distance over time. Time for a full sweep, a full turn, a full orbit is called the period. We just denote that by t. Let's clean up the board now. So we're looking at Kepler's third law. I need all my space. Well, this could be a point, but I just call it a mass because it's easier to think. And suppose this mass is moving with a tangential speed v. It's experiencing a centripetal acceleration towards the center of AC. That's applied by the gravitational force, because this acceleration is the acceleration due to gravity. At any point here, this mass is experiencing the acceleration due to gravity, even though it has this velocity v. So you can think of them as being balanced. Some people say it's not the right way to think about it. It's okay to think about it that way. G is pulling in, and centripetal acceleration tends to push you out that way. If you're in a car, you tend to get pushed that way. Centrifugal, actually. We'll talk about that later, the argument between centripetal versus centrifugal. So, if we can say G can be equated to AC, we can write V squared over R is equal to G M over R squared. So for V squared, we can put in what V is. Pi r over t is the v, and we squared, we get 4 pi squared r squared over t squared. And we have a result that's going to have a t squared in it, and it's going to end up with an r cubed in it, and we will see that it turns out to be Kepler's third law. Now we can cancel 1 power of r, now we'll multiply both sides by r squared. And what else will we do? Let's see. We'll divide both sides by gm. No, I'll leave it there. I'll leave it this way. Okay, so let's see. Yeah, we'll divide both sides by gm. We'll multiply by t squared, actually. I'm making this too complicated for you guys. Look, it's very simple. I was trying to do too many steps for you, and in the process, missing the point. Using this equation here. So I'll substitute in for the v squared. I'm going to have 1 power of r here. I'll bring the r squareds up here. And the t squareds up here. And that leaves me with Kepler's law. T squared divide both sides by gm to cancel out the gm's. So now we get t squared is k times r cubed, and k is the constant that we didn't know before. So we get Kepler's third law as a consequence of Newton's theory of gravity. We'll do one more result. This result I will use over and over again when we do relativity. As usual, we have to have a circle with a radius and a mass. It's a gravitating body. Alright, so we want to get an expression for the escape velocity. What does that mean? It means that if you have an orbit that doesn't remain circular, but the object can disappear off into outer space and not close in on itself again, okay? So you need enough kinetic energy to overcome the potential energy that's involved here. In other words, the kinetic energy that this mass has in orbit is going to be enough to overcome the potential energy. Now the kinetic energy of any mass m with the speed v is a half mv squared. It's a scalar. mgh is the potential energy near the surface of the Earth. If we take an object of mass m and lift it from here to here, if the acceleration due to gravity is g, the force is mg, and the work done lifting the mass is force times distance. But mg is the force and h is the distance. the work done is mgh when you lift the mass. Now let's consider what happens, and this is not the right way to do it. The right way to do it is to work out an integral, but we don't have that math available. It's a hand-wavy argument. We're going to ask what the potential energy is of an object if it's up here. Alright? Well, its kinetic energy is a half mv squared. Its potential energy is also mgh. But here's the h. I began with this mass down here, let's say, and I lifted it all the way up here. R plus its altitude, right? This whole distance we'll call R now. In other words, from here to here is the orbital radius from the center of the Earth, okay? If these were two gravitating bodies, Newton's law would involve this R, not this R, not this R, this R, the sum of the both of them. So, we'll call that the height h. We moved up from here to here, that's the distance you moved, and you did work. Bringing the particle from the center of the Earth up to this height required work of force times distance. And the distance covered was the big R, and we'll call that the potential energy stored in the object by virtue of being at that height. Now one pair of R cancels and we're left with R on the bottom, just R. So now we have an expression for the potential energy, and that's for the kinetic energy. Just when it's about to get to the situation where it can escape, we'll say that the potential energy and the kinetic energy are equal. Just at that point where the object is just about capable of escaping away. And so we'll say that half mv squared, its kinetic energy, is equal to the potential energy. We can cancel the little m's again. Solve by multiplying by 2 and taking the square root, we get an expression for the escape velocity. As an exercise at home, put in the radius of the Earth, put in the mass of the Earth and work it out. The mass of the Earth is 6 by 10 to the power of 24 kilograms. The radius of the Earth is 6.37 by 10 to the power of 6 meters. Put those guys in and you get the escape velocity at the surface of the Earth. If you want to know what the escape velocity is for the space shuttle in orbit, you have to add that extra little bit. Okay, so what else? If the speed, the escape velocity, if the escape velocity is this speed, and that can happen. If n is really large and r is really small, or either one, if that happens, and this in meters per second is a speed of 3 by 10 to the power of 8 meters per second, if the escape velocity is this big, then the escape velocity is in fact the speed of light. Okay, now this was first thought about by John Mitchell. If the escape velocity of an object, if an object has a big enough mass or a small enough radius, then the escape velocity is huge. And it's possible that maybe light can't escape from this object. If the escape velocity is greater than the speed of light, we'll say that the object is going to be dark. And John Mitchell, who lived between 1724 and 1793, first talked about dark stars, nowadays called black holes. Now we could ask, what radius would the sun have to shrink to in order to become a black hole? We can rearrange this equation to say R has to be 2 times G times the mass of the sun over c squared. If you put in all the numbers, you will find that our sun shrinking to become a black hole or a dark star will be 3 kilometers. We'll do that calculation next time.